Hi, and welcome to my talk about using Flink SQL on Ververica Platform. My name is Ingo, and I work as a senior consultant at T&G Technology Consulting here in Munich, Germany. I like working with Java and TypeScript, and I love open source, so I was very happy to join Ververica in April 2020 to support as a full-stack developer. There, I work primarily on Ververica Platform, the commercial offering, with a focus on the SQL integration that we're about to take a look at. By now, I'm also part of the SQL team at Ververica, meaning that I work on open source Apache Flink as well. Now let's talk a bit about our goal with Flink SQL on Ververica Platform. We wanted users to be able to explore the data interactively, as well as develop their pipelines with as much context as we can provide, and then help the users to bring those pipelines into production by deploying them into a cluster. To achieve this, we heavily rely on Flink's APIs and their extensibility. One of the great things about Flink is that in its core, it is agnostic to where data comes from. It has the concept of different connectors which define how to connect to specific systems to either read from or write to. In Table API and SQL, every table is then actually backed by a connector. Flink ships with connectors for the most popular systems already, such as Kafka, Kinesis, Elasticsearch, and so on. Similarly, formats define how to work with certain shapes of data, such as Avro or JSON. This is useful when a connector can actually work with different types of data, such as the case for Kafka. And that way the implementation of talking to a system is separated from the implementation of how to serialize or deserialize the data itself. In Ververica Platform, we include most of these as what we call prepackaged, meaning that no setup is required to make them work. You just install a platform and you can use them out of the box. However, if you are working with another system or in some context where you cannot use one of the connectors Flink provides you, you can also implement your own connector on top of the same APIs. Of course, we support this case, meaning that you can import custom connectors and formats and use them just like prepackaged connectors in the platform. We'll take a look at what that looks like in a minute. Catalogs sit one level higher than that. They act as a persistence layer for objects like tables and functions. For example, the JDBC catalog exposes a traditional database as a Flink catalog, where each table is backed by the JDBC connector. The default catalog in Flink is a simple in-memory catalog. In Ververica Platform, however, we set the default to our own persistent built-in catalog. The built-in catalog allows multiple users to collaborate by giving them a consistent view, and we'll talk about that more in a second as well. User-defined functions, or short UDFs, let you write your own pieces of logic, for example in Java, and then register them as a function that you can call from SQL. If none of the many built-in functions that Flink offers matches your requirements, or you just want to implement more complex logic outside of SQL, you can, for example, use UDFs. Of course, this is also supported by our platform, and you can simply import those functions and then use them. And last, but certainly not least, is our SQL editor. Really, this is the core of the user interface for Flink SQL in the platform, and it actually comprises various features utilizing Flink APIs. We'll talk about some of them in a second, but let's first actually take a look at the platform. So if you first open the SQL editor in Ververica Platform, this is what you will see. As you can see, there's not a whole lot going on right now. On the left here, we have our Schema Explorer. So this is where you can see your catalogs, your tables, your functions, and so on. By default, we have this VVP catalog, so there's already a catalog set up for you, which is using our built-in catalog. If we want to create a table in here now, I could just go ahead and write the DDL for this. But we also have a bunch of convenience features. For example, if I click on New here, you can actually see the different connectors that are currently packaged into the system. And if I, for example, select the DataGen connector, this will generate a skeleton DDL. And I could just validate this, for example, to make sure it is actually valid. If I'm happy with the statement here, I can execute this, and since this is a DDL statement, it will be executed directly in the platform, and you can now see that this table has been created and the Schema Explorer has updated. We can also see that this table is using the DataGen connector here, but if you want more information, we simply click on it and we get this detail view with the schema, the properties, and the DDL to create this object. As you develop your scripts here, of course, you don't want to have to copy them around anywhere, but rather just save them in the platform. So I can go ahead and save a script here in the platform directly. And also, if we head over to SQL scripts, you can see that I have a couple of scripts already prepared for this presentation. Now let's talk about the connectors. If we head over to SQL Connectors, we can see here the list of all the connectors that Ververica Platform ships with. We can also see the formats that are included, as well as the catalogs. If we want to add our own custom connector, we can simply click here on Create Connector. This allows us to either upload a char file or provide a URL to one. In this case, I will go with actually uploading a char. And this char contains two different connectors. So we have to make a choice which one we want to import. And for this case, I'm going to go with the IMAP connector. So this is just a little custom connector that allows you to read emails from a mail server using the IMAP protocol. Now, this will analyze this char or this connector and tell us whether the connector can be used as a source, whether it can be used as a sink, as well as list us all the options of the connector. Once we reviewed this and are happy with it, we simply click Finish, and this connector has now been added to the platform. So if we head back to the SQL editor here, and once again click on the New button, we will now see that the connector actually pops up here as well. And if I select it, it will generate a DDL statement or a skeleton of a DDL statement, and it will actually use the options of this connector here. So I can just quickly fill this out. Just to show one more example, if we select the Kafka connector, since the Kafka connector actually requires a format to be defined, we get the submenu here with the different supported formats. And let's say we choose Avro. And you can see that this automatically sets up the Kafka connector with the Avro format, and also gives you all the other options of the Kafka connector, including their documentation. Now, let's talk about the built-in catalog that we ship with the platform for a second. It provides an out-of-the-box way to persist your tables, views, and functions across users and sessions. It also uses the persistence layer of the platform itself, which makes it very lightweight and fast. One of the issues, however, is that between connectors, formats, and UDFs, there are a lot of extra dependencies potentially needed to run a job. And transferring chars from, for example, an S3 bucket to the cluster is a pretty expensive operation. If we simply added all the dependencies to every job, then things would be quite slow. So we want to figure out which dependencies are actually required to run a job, and then only ship those to the cluster. Similarly, some planning operations, such as the validation of the queries that we just saw, actually happen within the platform itself rather than going through a cluster, and only pulling in the use dependencies into the class loader needed for that helps avoid class loading collisions. Now, the catalog interface in Flink, on which the built-in catalog is built, allows us to provide our own factory for when the source and sink tables are created. And this allows us to hook into this process and prepare custom class loaders, which pull in the required dependencies. This gives us the information for connectors and formats. And in fact, for the prepackaged ones, we can even cache those class loaders as they are global to the entire application. For UDFs, we have a similar mechanism. We try to load classes from the current class loader when possible, and only fall back to loading in the dependencies when needed. If that happens, we once again record this in a separate class loader. This essentially gives us a hierarchy of class loaders which are tied together into the class loader we use for the underlying table environment. Since we control those class loaders, we can simply inspect them and then ask them for the dependencies that they needed to load. And this gives us a complete and exact view of the required dependencies that we need to ship to the cluster. So let's go back to the platform and take a look at how we can actually use this to explore our data. So if we head back over to the SQL script here and open the script, you can see here a small table, temporary table that I prepared. So this uses the DataGen connector, which simply generates random data, and it will actually generate one row per second and it will generate one column, which is a digit between 1 and 9. So let's say I want to actually see the data in this here. I could simply go ahead and do a select from random and just like you're used to from traditional database systems. Now, in this case, to execute this query, we actually need a Flink cluster to execute it against. So if I hit run here, the platform will tell us that we need to set up a preview session cluster. The reason we use a session cluster for this functionality of exploring your data is that session clusters can continuously run in the background, and that makes deploying these jobs very fast. So if we head over to create session cluster here, you will see that it actually pre-fills some information. And for example, it also sets some configuration options for this cluster that we recommend you do set for a session cluster for this purpose, just because you want to have multiple people running these previews in parallel, things like that. Now I'm actually going to not create this cluster here. I already have a cluster prepared, which is already up and running, so we don't need to wait for it. And I can simply go into the configuration and annotate this session cluster for usage with the SQL editor previews. So let's head back over to the SQL editor. And let's actually open up our script again. So we want to simply take a look at this data. Now that we have a session cluster up and running, if we run this, you will see that the window here pops up and this job will now be deployed into the session cluster. And we can see that every second we get one digit coming in between 1 and 9. Now I can also go ahead and pause this query here, which will simply stop the front end from querying more results from the back end. And we will talk about how that works in a second as well. And of course, I can also cancel the query here. Now, another thing is that you can see that we have this results pane and a changelog pane here. So the changelog pane is actually the results as we get them from Flink. And in this case, this is pretty simple because we just select an incoming stream of rows that are all new, and this is called an insert-only or append-only stream in Flink SQL. Now, let's make this a little bit more interesting. So let's say we want to actually group by this number and generate a count. So we want to count how many times each digit has occurred. So in this case, in a traditional database system where all the data is readily available, you would just expect to see the final result. But in streaming SQL, since the data comes in over time, we can actually see that the digits coming in first start out with a count of 1, but then over time the count actually updates as the digits get repeated. Now, if we head over to the changelog for this, we can actually also see this in action. So the first couple times we see that a new row is coming in. And then, for example, here, the digit 5 came in with a count of 1 the first time around. And now digit 5 was produced again. And this time, Flink will actually generate a retraction here, which will remove the row that previously existed and then push a separate change to update this. When we accumulate these results or materialize them, this is what we see in the results pane over here. So as we've seen, we need to have a session cluster annotated to be used for executing these previews. What we then do is we add a sidecar container, which we call the result fetcher, to the session cluster. The result fetcher maintains a small queue of data and back pressures when that queue is full, keeping the state in this container small and therefore reducing the resource footprint. Flink offers an API to collect results from a sink, and the result fetcher uses a modified version of this to retrieve the results directly from the session cluster. Now, as we just saw, what we actually get from Flink is this changelog stream, and the materialization of this happens on the front end side. Browsers can actually handle quite a bit of data here, but just to not crash the browser if a user goes for coffee, we automatically pause the preview when reaching 100,000 rows. This should be quite enough to get a good understanding of the data anyway, but if you really need to run it for longer, you can simply resume the query again and it will continue running. Now, while the browser can deal with quite a large amount of data, it isn't quite as good at rendering that out. So to keep things smooth, we use virtual scrolling, meaning that only the portion of the results that is actually visible on the screen gets rendered into the browser. And one important thing is to cancel preview jobs when they're not needed anymore. Since in their nature, Flink jobs can run indefinitely. So if a user cancels a preview or starts another preview, we automatically cancel the underlying Flink job as well. The result fetcher has an in-memory storage per job. So apart from the actual fetcher process, it also keeps a timestamp of the last time the frontend has asked for more results. And this gets updated on every request. This timestamp is important because we cannot always rely on users to cancel a preview job explicitly. For example, if the browser is just closed, or maybe somehow the connection is lost, we wouldn't be able to cancel the job. So with this timestamp, we can periodically look for such expired jobs and then just cancel them if a certain amount of time has passed. That also means that pausing a preview for too long will actually terminate the job, but you can always just restart it. Another periodic schedule in the result fetcher looks for orphan jobs and then cancels them, meaning jobs that are preview queries but aren't registered in the result fetcher. And this can happen if the result fetcher restarted for some reason, since it only keeps the state in memory. Basically, we cancel all running preview jobs unless we can prove that they are still relevant, just to avoid clogging up the cluster resources. This operational mode, of course, wouldn't work for productive pipelines, and regular deployments in the platform are, of course, not handled like this. We simply do this here because preview jobs are intended to provide quick insights into data and evaluate SQL queries on a qualitative level, but not to achieve the same stability, resiliency, or throughput of productive jobs. Now, let's head back over to our editor here, and we have added our own custom connector earlier. So I've prepared another little SQL script here, and this is actually setting up a temporary table, which makes use of this connector that we just added. Now, I did modify this connector slightly to not actually require a password for obvious reasons. This email account that I'm using here is subscribed to the Flink mailing list, so it has quite a few emails. Now, if I go ahead and just select from this, we will see that this connector is now actually working, and we can see emails coming in here. Nice. So we can see we quickly go through all the emails that have accumulated in this email account. Now, just to show that, of course, we aren't restricted to only select, like only looking at a table directly, we can, for example, also use an aggregation query. Like here, we window over the timestamp of the emails to see how many emails have been sent on a particular day. And this will work just as well. And you can see that everything is pretty fast and snappy. Now, what if we want to actually write a pipeline and deploy this somewhere? So we no longer want to look at the data, but we actually want to write it somewhere. So let's say we want to write into a sink. And for simplicity, I'm just going to select everything from this table. Now, this table currently doesn't exist. And if I validate this query, it will also tell me that it doesn't exist. So something that we offer here is the ability to automatically generate a skeleton DDL, just like we did over here. But this has an addition of automatically inserting or inferring the schema correctly. So I'm going to use the black hole connector, which is kind of like a trash can connector that just discards all the records. And if I click this, you will see that it actually took the correct name that I intend, as well as take the schema from the query that I'm actually trying to write into this. So for example, if I didn't select all the columns here, but say only the UID and the subject, and I try this again, then this time if I generate the statement, the schema will be inferred correctly, and only the UID and the subject will be added to the sync schema here as well. Now, let's just actually execute this real quick. So we have now created this sync here. And if I validate this query again now, you will see that this time it can validate successfully. So if I want to execute this now, there's nothing to preview, so we cannot use the preview functionality from earlier. In this case, we actually have a pipeline that we want to deploy. So this time around, if I click run, the platform will actually tell me that I need to create a deployment for this. And this brings us here, and I can select where I want to create this deployment on. I can see the query again, I can give it a name. And basically here we step into the regular realm of managing deployments in Ververica Platform. So I create this deployment now, and it will automatically start up this job, which will take just a couple seconds. And then we can also see that in the center here, we have this graph. So you might be familiar with the operator topology graph from the Flink UI, which of course we also have here on the job graph. This is a simple job, so there's not much to see. We also show this graph, which is basically a topology graph from the table SQL perspective. So we can see which source tables are used in this job and which sync tables are used in this job, as well as some information about the job itself. And that basically brings us to the end. So we've seen how in Ververica Platform, we can use prepackaged connectors or add our own custom ones, write queries and have them validated, preview them to explore data interactively, and finally bring a pipeline into production by deploying it into a cluster. Thank you very much for listening in on this talk. And if you have any questions, I'm more than happy to answer them.